Alright, this is the last video on chapter 23 in the Birch book. This is on isomerism or isomers. So we're going to talk about, we've talked about the chain, aromatic type compounds. We've talked about the functional groups. We've talked about naming those compounds. And then we've talked about different types of representations of those compounds, whether it's molecular formula, structural formula, condensed structural formula, ball and stick model, or the line bond model. So isomerism is really important. This is what you will spend a lot of time on when we're talking about just compounds in general in organic chemistry, because one isomer may be beneficial to the body and the other isomer may be deadly. So we see that, it seems like, quite a bit, where one isomer, one structural formula is beneficial and the other structural formula is detrimental. So we're going to talk about what isomerism is, and then we're going to show examples of that. So the first thing we want to talk about is structural isomers. These are also called constitutional isomers, and it's when you have the same atoms, they're connected together, but they're connected in different ways. And we've seen that already. If you go back to the last video, we saw octane, and then we saw methylheptane, and they have the same molecular formula, but they are structurally different. And because they're structurally different, they have different chemical and physical properties. So here's some examples. We have pentane at the top here, and it's, again, this should be, I hope at this point that this seems pretty easy to think about, that it's, if you see something that's 5 carbons long, then you know that it's pentane. If it's just carbon and hydrogen, this is an unsaturated, means there's no double bonds or anything like this. This is a saturated carbon here. So saturated carbons, carbon and hydrogen, and we can represent it by structural formula, and then we can also represent it by the bond line formula, bond line model, and then we can have a ball and stick model. So again, we've talked about what the advantages of each one of these models are. Again, I think you'll see a lot of this. I think you'll see a lot of the bond and line model. And then they talk about the boiling point to show you that these compounds that have the same molecular formula but different structural formulas or constitutional formulas will have different physical and chemical properties. So in our next example, the longest chain is these 4 carbons, and now we have a methyl group attached to one of the carbons. So again, same molecular formula as pentane, different structural formula, and this is the way we represent the compound with the bond line formula. Again, each one of these corners ends represents a carbon, and carbon has to have 4 bonds. So off of those carbons, there are hydrogens to make it have 4 bonds. Ball and stick model gives you more information, much harder to draw though. And you can see that the boiling point is less here. The boiling point is less. And if you get back to, this is why all this chemistry is related. If you go back to Gen Chem 1, there's a whole chapter on, chapter 11 on intermolecular forces. And so what type of force do you think is happening between these molecules of pentane or methylbutane or 2,2-dimethylpropane? You can answer that, you're in good shape. I like to hope that from Gen Chem 1 that you can go, oh yeah, this is these are nonpolar molecules This is London dispersion forces, or just London forces. That's the intermolecular force between the molecules, and it's based on instantaneous dipole moments between the molecules. Other things that come into play here is the fingers. These, you can see that there's going to be, if I have two of these, there's possibilities for these kind of another molecule to kind of interlock with this one. And so, again, we're going to have a higher boiling point to separate one molecule from the other one. Notice as this has a branch chain, it's starting to look more spherical in nature, and that makes it easier to separate one molecule from the other one. And you can really see it here. This is starting to look like a true sphere, right? And so it has the lowest boiling point, much easier to separate these molecules. So I hope that kind of, refreshes your memory about Chapter 11. You may want to read about that. Again, what are we trying to do here? You're finishing up Gen Chem 2. You've seen all of general chemistry. You've seen the tools. You understand why we've done this. And now you're ready to go on to either your physics classes or your organic classes, or both. Or an analytical chemistry class, and you understand why molecules in general behave the way they do in the large. We get into more specific things later on, but that you have got the tools now to start investigating different aspects of chemistry. So this last one, again, only you see a methyl group here and a methyl group here, again, also called alkyl groups in general. These are what we call R. There's an R group here. It's still the same chemical formula. Molecular formula, I should say, specifically. Again, what's the difference between a chemical formula and molecular formula? When you say molecular formula, you're conveying that, hey, this is a covalently bound compound. Chemical formula, you could call it that. It's just not as specific. All right. So here, same molecular formula. This is called 2,2-dimethylpropane. Longest chain is 3 carbons. Again, I like these newer names, but again, it's up to the professor. It's up to what the preference is. And again, this one is called a lot of times N-pentane, which means normal pentane, which is a straight chain. And then isopentane tells you that there's a branching effect happening there. And then neopentane, we get this tertiary carbon there. All right, so constitutional isomers have the same molecular formula, different structural formulas, which we can represent 3 different ways here. And the effect of these changes in the structure affect chemical and physical properties, and we're showing a physical property boiling point here and how it's affected. And again, when we talk boiling points, it is the intermolecular force, the force between molecules, that determines the boiling point. And the more spherical in nature the molecule is, everything else being held constant, all these have the same molar mass, the lower the boiling point. It doesn't take as much energy to get that to boil. All right, so the next type of isomer is called a stereoisomer. And they contain identical bonds, but differ in the orientation of those bonds in space. All right? Identical bonds, but differ in orientation of those bonds in space. So there's 2 types of stereoisomers. There's geometrical isomers and there's optical isomers. Geometrical isomers occur when compounds that have restricted rotation around the bond. So what does that mean? Generally, a single bond, if you just have a single bond and there's a carbon here and there's a carbon here, and then you have hydrogens coming out like this. This is going to be a tetrahedral here. And then you have the same thing here, carbons coming out like this, or hydrogens coming out like this, I should say. Then you get something like that. Well, this single bond doesn't have restricted rotation. The carbons can twist where the hydrogens are in line with each other. It can also twist where they're off center, like if we would superimpose. If we're looking down this way, we could see that this hydrogen is in this blank space here on this carbon. So it's a rotation of what, like 30 degrees. So geometrical isomers is where this is restricted. There's no rotation. And so that's going to occur once you have something like a double bond. So once you have a double bond, those carbons cannot rotate. And so you have a fixed or restricted rotation around the carbons. So with the geometrical isomer, things that we're going to look for is if we have like a chlorine here, maybe a chlorine here, are they beside each other or are they across from each other? So this is one isomer. The other one would be the chlorines up here and the hydrogens down here, and now they're across from each other. So that's what they mean by geometrical isomer. You have a restricted bond, and it's a fixed molecule, and then we're going to look at, we're going to give those names, all right? So a stereoisomer that are mirror image of each other are called optical isomers. All right, they're not superimposable. They're not superimposable. So we're going to see examples of those on the next page. But you got to speak the language. Stereoisomers contain identical bonds but different orientations of those bonds in space. And the two types of stereoisomers that exist are the geometrical isomer, where the bond is fixed, and so therefore there's restricted rotation. Generally, and again, double bonds are a good example. And then optical isomers, where you have a mirror image of something, but they're not superimposable. So we're going to see that. All right, so these are geometrical isomers. You have a double bond here, so that restricts the rotation. These carbons can't flip around. And so we end up with 3 different compounds here. And they all have different chemical and physical properties. Now they all have, different chemical and physical properties. When the chlorines are beside each other, like this, we call it cis, all right? When the chlorines are across from each other, we call it like transatlantic, trans, all right? And then when they both are on the same side, we just call it 1,1 dichloroethylene. And again, why is it called ethylene? If there's a double bond in the compound, it's not an alkane, it's an alkene. And alkenes have that double bond, so that's why they all end in E here. And when you say cis, we know you're saying beside, so we don't have to say like 1, 2, or dichloroethylene. Cis means beside, trans means across. We know just based on this prefix that we know that what it looks like. So these are stereoisomers. They have the same bonds. Nothing's changed on the bonds. It's just different orientations in space. And these are geometrical isomers because they have a fixed rotation. Now this is the coolest thing in stereoisomerism. All right, so let's look at this. This is to me, this is just really neat. So here you have a carbon in the center, and you have 4 different elements bonded to the carbon, so that's why it's a tetrahedral arrangement. And they're the same though. This is oxygen, this is oxygen, maybe this is a nitrogen, this is chlorine, and I'm going to assume that one's sulfur, okay? So here we go. We have 4 different elements bonded to the carbon, and there is no way, and they're mirror images of each other. So just think of this as the dividing line. This is the mirror. They're mirror images of each other. But they're not superimposable. There's no way you can bring this over to here and it fits this exactly. Because you can see, if I bring this over, I would have a red ball here, and I would have the blue ball here. And yes, the yellow would still be the same, but these are not the same. This would be the red one. We'll call whatever I said this is oxygen and this is nitrogen. So they're not superimposable. I don't care how you rotate it. This is never exactly the same as that. This is where we get into maybe this one's beneficial to the body and this was detrimental to the body. It can cause problems like that. So they are stereoisomers. They are optical isomers because they are non-superimposable. Non-superimposable. And we call, when you have the carbon like this and you have non-superimposable images, the term that you want to use here is chiral. All right, chiral. So if you see two carbons with 4 different things coming off of it, and they're mirror images, we would say those are chiral. These are the chiral centers of the atom, and they, from that center, you can see that they are mirror images of one another, but they're not superimposable. So spend some time on that. Read about that in the book. This is probably, it's one of the more important isomers that we deal with. So you want to definitely understand chirality, stereoisomerism, optical isomers. So what do we mean by optical isomers? Well, molecules with non-superimposable mirror images are chiral, and a pair of such mirror image molecules are called enantiomers. So what we just saw was enantiomers there. So you need to know this term. Speak the language. So these words convey to another chemist that, hey, we have non-superimposable mirror images, and there's a pair of them, and they call them enantiomers. So keep that in mind. All right, so then we're looking at this, and it says it's often necessary to represent tetrahedral molecules three-dimensional on paper, a two-dimensional surface. Now, I actually talked about this in Chem 180. I hope that you've done this already. I mean, Chem 170, Gen Chem 1. I hope you've already done this by the time you get to Gen Chem 2. If not, here's where you're going to learn that we have, I'll do methane real quickly here. So here's what we should have learned in Gen Chem 1. You know that this is a molecular formula. This is methane. You know that the Lewis structure for this looks like this. All right. So we can do a Lewis structure. We have a total of 8 valence electrons, 4 from this carbon, and then plus 4 times 1 for the hydrogens. And then you should have had in Gen Chem 1 that the classification, this would be AX4 or AB4. This changes with different people, but AX4 means 4 bonding groups coming off the central atom. I like X because it's bonding groups, it's not bonds. And I think the bond B sometimes means bonds. But remember, in VSEPR, valence shell electron pair repulsion theory, you don't distinguish between a single, double, and triple bond. So if it's AX4, how do you keep 4 things as far away from each other as possible? Well, you put hydrogens that are 109.5 degrees apart, which is greater than 90. So that's the problem with, you say this is what the geometry looks like. This is a larger angle. And then to convey that in this tetrahedral that the hydrogens coming out of the board, we use a triangle. All right, and the triangle says, hey, it's coming out of the plane of the screen. And then we use a dash line, and some people get real fancy with their dash line. They actually do a triangle with the dashes like that and put a hydrogen like that. I don't care. You can just use dash lines. That's fine. But that conveys that that hydrogen is behind the plane of the screen. And so it's important. I can't stress enough in organic chemistry that you draw a structure correctly, and that you try to approximate those angles 109.5, because In organic chemistry, you're going to be looking at reactivity sites, and it's, you know, the reactivity sites are going to be based on those geometries. Like, what, you know, can something get in there and react with it? What are the charges at those points, and so forth. So they give you a couple examples here. So again, it's really, um, I don't quite like the way this is represented. It looks like the chlorines are coming out at you because it's kind of rotated. But again, what this tells me is this is all in the same plane. All right. And then this hydrogen's behind the plane. There it is, that one and that one. And these two are coming out of the plane. I wish they would have maybe rotated a little bit back this way to make it clear. But these two hydrogens are coming out of the plane. And so that's why we use the triangles for those. Okay. So dashes for things behind the plane, triangles for things in front of the plane, solid lines for those things in the plane. I hope that's not new to you. I hope you've heard that before. I think it was really important when we did molecular geometries in Gen Chem 1, and I hope you had heard that when you took that class. Here's a question. Are these two things isomers? Are these two things isomers of each other? And the answer is no. They're not the same thing, so they're not isomers of each other. Just thought we'd check out, just make sure. All right. So stereoisomerism, one property of chiral molecules, again, where we have four different things coming off the central atom, is that the two enantiomers rotate a plane of plane polarized light in opposite directions. They are optically active. All right, so what this means is that we're going to take a light that's in one plane, maybe it's up and down like this, and we're going to pass it through this chemical in a tube, and then this is going to rotate one way or the other. So this either rotates this way or it rotates this way. And that's what they mean by optically active. The enantiomers are optically active. And you go, why do I need to know this? Well, this is how you separate these two substances. Once you see that one is rotating one direction and the other is rotating the other direction, then you're going to get, that's going to give you an indication that you do have optically active enantiomers with chiral molecules. And it gives you more information about the substance. So here's what you need to remember. If the polarization is rotated to the right, we call it dextrorotary. And if it's rotated to the left, we call it levorotary. So dextro and levo, that is how we know we have two. That's how we explain the two enantiomers and how they're different. So enantiomers always rotate the light by the same amount, but in opposite directions. If you have here's the thing: if you have an equal molar mixture of both, they're called a racemic mixture, and there's no net rotation. So if you have equal amounts of both D and L, then you're not going to see a rotation. That's a racemic mixture. So you need to know that term. And that's pretty rare, but it is there. Racemic mixture, all right? So racemic mixture means you have equal molar amounts of both enantiomers. So they do a much better job than me drawing a picture here. So this is what it looks like. You have a light source. You have a polarized lens here. So it only allows light to travel in this vertical configuration. We pass it through a container of the particular enantiomers, and if we look back on this other side, and we can adjust this filter here till we see the light, and that way we can figure out what degree rotation it is. So what would happen here is this light would be pretty much knocked out, right? Because its plane has changed. And so you wouldn't see anything. Just if you've got some polarized sunglasses at home, look how you rotate the polarized sunglasses and things darken and things lighten. We're doing the same thing here, and then we can figure out to get it back to a full brightness of light like we saw here, we can determine what that degrees is. And that's how we determine, what the, first of all, that it is optically active, and that we can classify it or use it. Here again, what do we do in chemistry? We try to classify molecules, and that tells us the degree of rotation. It tells us more information about that enantiomer, or that stereoisomer, if you want to think of it that way. All right, that concludes chapter 23. It's mostly been about naming basic structures, different types of models, functional groups, and isomers. And that's where we're going to stop, because the rest of this chapter is about reactions, and that takes a little bit more skill, a little bit more knowledge, and I will leave that to your organic professor to start introducing things like nucleophilic reactions, or substitution reactions, or addition reactions, and so forth. All right. So I hope you enjoyed this chapter. It's definitely a change from the rest of Chem 180, Gen Chem 2. And again, the reason why I chose this chapter is that generally at the end of the semester we have an optional chapter, and I wanted to do just a brief introduction to organic chemistry, especially the naming, so that when you take organic chemistry, you're not just going in blind. You know about equilibrium, you know about kinetics, you know about acids and bases, and now you know a little bit about molecular compounds, organic compounds, and hopefully it also ties in kind of the holistic thing of general chemistry that, again, noticed in this chapter. I hope you noticed in this chapter, we've said it over and over, that a lot of things in this chapter, organic chemistry, is tied to what you learned in Gen Chem 1. So you can't just forget Gen Chem 1. They're not compartmentalized. You had to know Lewis structures and molecular geometry and intermolecular forces in this chapter to describe what's going on. And then in Gen Chem 2, you have to know about kinetics, equilibrium, whether it's acid-base equilibria, solubility equilibria. You have to know about that in order to explain how far a reaction's going, how much product's going to be formed, and so forth. And then we talk about the energy of that through thermodynamics, and we brought in a new term, entropy. Entropy is a driving force for chemical reactions. And then the last part here is organic chemistry to, again, set you up for the next class. So I hope it's been helpful. If you have questions, email me.